Hello everyone, my name is Angelo. Welcome to this tutorial. I'm gonna teach you the techniques needed for your lab assignment, but of course using a different data set. So you can apply these methods to the college data set in your lab. This involves data imputation, visualization, correlation, subset analysis, and data splitting and cross-validation. I'm gonna use the Boston data set, which includes housing data for Boston neighborhoods. Key variables include crime rate, average rooms per dwelling, median home value. So make sure you have the required packages installed. So for example, in here, I'm gonna use this MASS package to get access to the Boston dataset. So you don't need to install this one for your homework. But if you wanna follow this tutorial, you're gonna need it. And also this core plot package, we're gonna use it to plot the correlations between some variables. So first of all, we need to install these two packages. Then we are gonna load the Boston dataset, and I'm defining here this df variable as our dataset. So with this code here, I'm inspecting the variables in our dataset and the type of those variables. So as you can see here, we have 14 different variables or columns and 506 observations of or rows in our dataset. And all these variables are num for float numbers and int for integer numbers. And given that the first section of your homework asks you to list quantitative variables, I'm gonna add some non-numerical variables into our data set just as an example. You don't need to do this for your homework assignment, but this is just only to give you an example. So I'm creating here this random string variable, which is simply a random selection from this list of character values. So I'm gonna run this here so we can see now that our data set has a new variable or a new column, and the type of that variable is a character variable. So now we are ready to list our quantitative variables, and this is really important because sometimes we have this combination of different type of variables in our data set. So what I'm doing here is just filtering the names of the variables in our data set using this function over here. This sapply function in R is part of the apply family functions designed for applying a function to each element of a list or a vector. So what I'm doing here is saying, okay, from all the variables in our data set, just give me those that are numeric. So we can see here in this output that the new variable that we already added as a character variable is not included in this list. So we can do in the other way. So for example, we can ask just only for those variables that are character or non-numerical values. So in that case, we're gonna get just only this random string variable. So this was just only to give you an example. So now we have all our quantitative variables in this variable here. Then we need to inspect for missing values. And again, due to this Boston dataset, doesn't have any missing values, I'm gonna add some, just to give you again an example. So in here I'm saying, okay, for this particular column and this one, I'm gonna add some missing values. So once we count all our missing values using this function here for each column in our data set, we can inspect in which columns we have these missing values. So these numbers here, of course, corresponds to the number of missing values that we added before into our data set. So that's the first thing. We can inspect the number of missing values that we have in our data set in each variable using this function here. But now we need to replace those missing values using some imputation methods. So for this example, I'm going to use the median, but there's a different methods that you can use, and actually you should discuss some of those alternative methods in your homework assignment. But for now, let's go through this for loop. So this is very intuitive. So for each quantitative variable in our data set, I'm gonna ask which of those variables contains missing values, and in that particular positions, I'm gonna fill that that positions with the median of the values of our entire column. This argument here is very important because if you don't add it, you're gonna get a missing value over here. So let me show you just this as an example. So if you run only this command here, of course, the R language cannot compute any numerical value using missing values because the R language doesn't know how to interpret these missing values in a mathematical operation. So what we are doing here is saying, okay, if you find some missing value within this particular column in our data set, just remove it. Remove those missing values. And by doing so, we are able to compute the median as a numerical value. And that's it. So then we can check again if we have missing values after this imputation using the median. And as you can see here, we don't have any missing values now in our dataset. Okay, section 2 is about box plots. So we are going to use a for loop and at least 4 colors, that's the requirement. So we're going to use the Boston dataset to practice again. So let's select in here 4 variables and plot them with some labels. So we set a 1 row and 4 columns grid using this part function with this argument over here. So the for loop in here plots each variable using the xlab for variable names and cycling through 4 colors. That's what I'm doing here in this for loop. So you can also use this PNG function that comes with this other function here if you want to store in your hard drive the plot and use them eventually into your report. And also you can customize the dimensions of this file depending on your preferences. So let's comment this over here just to plot the 4 box plots. And then if you can use this one just to store the file in your hard drive, so we can just check here the file that you can generate independently using this PNG functionality. Okay, the next section is about correlation plot of quantitative variables, and you need to also provide some interpretation. So in here we're going to use the core plot function and the core plot package to visualize correlations again in the Boston dataset. So this is very simple. We're going to use this core function to calculate the correlations between all the different variables in our data set, and then using this core plot we are gonna see the correlations in a visual form or in a visual way. So this plot shows the correlations, and in blue we have the positive correlations, and in red we have the negative correlations. So darker colors indicate stronger correlations. So for example, this variable over here, which is the rooms, has a positive and high correlation with this other variable here, which is the median home value. And this makes sense because as more rooms in a house often increase its value, right? Okay, so next section involves subsetting. So we're gonna subset neighborhoods near the Charles River, and we can do this in this data set using this condition over here. We can set this chas variable equal to 1 to subset neighborhoods near the Charles River, and then just filter the data set, our data set, using that condition. And in here I'm just counting and some all the observations that meet this particular condition, and that's it. Same thing if we want to count near and not near river, so it's just filter our data set using the same variable. If this variable is equal to 1, that means that the neighborhoods are near to the Charles River, and if this chas variable is equal to 0, that means the opposite. And at the end I'm just summing all those observations that meets those different conditions. In here we have the box plot, which compares median home values, and that's it. In here we don't have a lot of things to explain because this is very similar to the previous box plots that we saw before. And for this part, the only thing different is that we are using the mean of these values here to calculate the percentage, and we can compare also numerically these differences. Exactly the same thing that we are doing here, but graphically. In this next section is about data splitting, and we need for this section a function that I call f split to split the data set into different percentage for training data and test data. So in here, I'm establishing the seed. This is only to ensure reproducibility. This is a good practice when you run some random functions. Uh, so this ensures that your results that you can get will be always the same, given the fact that you are establishing this seed here. Then I'm getting the number of rows and the percentage of those rows that represents the number of observations in our data set. So basically here I'm saying, okay, I want to split, in this case, the 75 percentage of our entire data set as a training set, and the rest of the observations, I want to use them as a test data set. And at the end, I'm returning these two different sets within a list. So the last section is cross validation. So for this part, again, we need a function. So this function shuffles rows, splits them into 10 folds, and returns a list of train and test sets. So again, the seed, just to ensure reproducibility. Then I'm getting the number of rows, and then I'm calculating the fold size given the number of folds that I'm gonna get. Then I'm shuffle my data set a little bit just to improve the quality of the observations that I'm getting in each fold, and then I'm just do the splitting part. In here I'm using this function, the rep function. This function is used to replicate elements of vectors or leads. So it's a really good tool for creating repeated patterns or expanding data in different ways. So what I'm doing here is saying, okay, I want each fold of each of this particular size until I'm reach out this length of our entire data set. And to finalize this function, I'm applying this apply. In R, again, this is part of the apply family of functions designed for applying a function to elements of a list or a vector. So I'm applying to our folds this list just to split or to have in each fold this structure, so I can access within each fold the test and the train datasets. And at the end, I'm returning the entire fold data. So this is just only an example. So we have 10 folds for this preparation for cross-validation purposes. And each fold has 450 observations for training purposes and 56 observations for testing purposes. And that's it. Thank you so much for your attention. If you have any questions, just let me know. Bye.